So the first one, and I'm going to go over what they're called as well, just so we know all the vocabulary. This one, oh, let me start by asking you, do you know what it would be called, like in a word form? Like this first one. It is a type of linear. So it's like a very specific kind of linear. Constant, good. And so what kind of a line is it? Because it is linear. Horizontal. And this one's going to be at -4. I just picked -4 just because you have to pick something. But believe it or not, this actually comes up a ton in calculus because calculus is the study of change, rates of change. And if something is constant, what does that mean? Not changing. So that's actually a huge thing when we start talking about velocity. Who's taken physics? Good shape. Okay. So this one is linear. Are you currently in physics? Took it last year? Then yeah. When we start talking about velocity and acceleration and all that, you'll be like, yeah, got it. Yep, you'll be totally good to go. All right, so this is in, your good old y equals mx plus b. You would start at -5. And then your slope is 2, so up 2 over 1. Do you remember this from Algebra 1 where like an entire month of your life was slope? If you can count to 2, you're good. But again, slope is a huge topic in calculus. I get that it's an Algebra 1 thing, but it's huge in calculus as well because that's your rate of change. Like a slope is a rate of change. So we talk a ton about slope. So that is a huge thing. Now we're going to do like behavior and characteristics of all these functions. You can't really talk about the behavior unless you understand what the graph looks like. So I put one of each of every type of function on here, just so we could do one of each. So what is this one called? Absolute value. I'm going to abbreviate. And it looks like a V. Let's review the transformations. Up, down, left, right, stretches, shrinks, all of that. What did this one do? Up 3, good. Right 1, because it's kind of backwards. So from the center, you're going to go up 3, right 1. That's the center of the V shape. Now you can always make a table of values. What do I get if I plug in 1? What do I get if I plug in 2? What do I get if I plug in 3? And that's not wrong. It's just a little bit tedious. Instead, you can use this 2 out front as your slope. So this is the center of the V. It's been stretched to 2 times its size. So instead of a slope of 1, you're going to do a slope of 2 in each direction. So it's like a narrower kind of V. So I went up 2 over 1 to get more points. Again, if you were like, I didn't really like that, that made me uncomfortable. Yeah, you can always make a table of values or just mentally go, what do I get when I plug in 2? What do I get when I plug in 3? It's just going to take you a little bit longer. The sharp point is an important thing in calculus as well. We're going to talk a lot about that. Like versus a nice smooth curve, having a sharp point instead. It does make a difference. These are those like bolded kind of absolute value bars. I will be impressed if someone remembers this, but I'm going to throw the question out there anyway. Do you remember what this is called? Oh yeah, good. Greatest integer, or it's the step one. So it's the one that looks like a staircase. Which I like bringing this one up too, because we talk a lot about continuity in calculus, and things being continuous or discontinuous. And this is a great example of something that's discontinuous because it's all broken apart. So this moved down 1. You're going to go ahead and go down 1 and put a point. So we're going to start there. And I stretched this one to make the stairs a little bit easier to see because otherwise they're super tiny. You have to flip this when it's inside. Do you guys remember that? So it's a horizontal stretch. Instead of by 1/3, it's a stretch by 3. So your stairs are going to be 3 units in length. So make them each 3 units in length. But they're still only 1 unit apart from each other. It's just like a staircase with deeper steps. I'll try and zoom in on that. Is that better? Do you remember how when we stretched it vertically, the steps were further apart from each other. So it would be like a staircase that would be like a big workout to have to walk up. But I like those. They're discontinuous. It's a really good example of that. This is coming back to us. I feel like some of you had true pre-calculus 2 years ago, so that makes me nervous for you. Just have good memories. All right, what is this one called? With this squared in there. Quadratic, good. And so it's a U shape, which is different from a V shape. Again, like whether it's a nice smooth curve versus like a pointed V, it does make a difference. So how did this one get shifted around, or like what are the transformations, I guess is what I'm trying to say. Down 4, good. And left 2, good. It's backwards. So down 4, left 2. And what's the other thing? So that's going to be the center. What's the other thing that happened though? It flipped. It's upside down. For the sake of time, I'm just going to kind of go like this. But, you know, you could plug in more numbers and like get more specific points, but it would be upside down. All right, so that one is quadratic with a squared. This one is square root. So they're inverses of each other. The only thing is when you take the parabola and turn it on its side for the square root, you don't get the entire parabola, you only get half of it. Why is that? Why do we only get half? Yeah. It'll break your vertical line, because it won't be a function. So it's going to be a parabola on its side, but just like half of it. All right, so how did this one shift? Down 5, good. Left 4. All right, so we're going to go down 5, left 4. And it got stretched by 3. Here I am going to make a table and try and plug in some more numbers. Okay, so we're just going to like mentally try and find some numbers to plug in. If you're like, I don't want to draw a table, that's fine. You don't have to. You can do it in your brain. But you have to be able to get a graph somehow. So you want to try and pick something so that when we plug in for X, we'll actually be able to square root whatever we get. Like you want to pick something that's going to like turn out pleasant. If you pick something that turns out unpleasant, you just pick something else. It's not a big deal. What do you want to try and plug in? 0 would be good. 5 would be good too. If we plug in 0, here comes your mental math. 0 plus 4. 4. Good. Square root of 4. 2 times 3. 6 minus 5 is 1. So 0, 1. And then somebody said 5 as well. So let's do that one. 5 plus 4. 9. Square root 9, 3 times 3, 9 minus 5 is 4. So 5, 4. And so again, you only get half of the parabola. You can always fall back on a table. You guys are hanging in there. This is awesome. So I put the quadratic and the square root together because those are inverses. I did the same thing with these two. What is this one called? Cubic, good. And then this one is cube root. And so they're like those wiggly things. One is upright and one is sideways. If you want to remember, the root one is sideways, like roots of a tree grow out sideways. Like if that helps you to remember it, the cubic is the upright one. All right, so this one moved. What directions? Up 1, right 2. Okay, so up 1, right 2. That's the center. And so it's going to wiggle like this. Let's try and get another point. What do you want to try and plug in? If we get something unpleasant, we will just pick something else. It is not a big deal. So 2 would be the best choice. We already did that one. Like this is where our point at 2 is. Our transformations got us there.
3.
3. So let's see. 3 minus 2. 1 cubed. 1 times 2 is 2 plus 1 is 3. So you get 3, 3. Now here's a trick so you can get the other point without having to do any more work. You can use the symmetry. Do you see how this is the center? Just watch me point to it because I kind of have a better explanation than here. Look, this is the center. Do you see how that one is up to over, kind of like a slope? You can do the same thing and go this way to get your other point. Just don't draw a line, like make it wiggle, like make it do like a cubic graph. And then we're going to do the same thing with this one, except it's going to be sideways. So this one didn't go left or right at all. It just went up 2. So you can have a point at 0, 2. And then let's try and plug in something else. 1 is a great choice. Keep it simple. So if you plug in 1, cube root of 1 is 1. Let's say for a second, though, you had to go further. What's the next good number to cube root? Because it's not 2. 8. What's your cube root of 8? 2. Do you guys know the next one? 27. After that, it starts to get pretty outrageous. The next one's 64. 125. Yeah, okay, cool. I was just bringing it up. Anyway, we're going to stick with 1. Cube root of 1 is 1. 1 times 4 is 4 plus 2 is 6. So you get the point 1, 6. And I'm going to do the same thing I did with the other one and use kind of like a slope. I'm calling it a slope for lack of a better word, but just like the symmetry. Do you see how those are 4 units apart from each other? So just go 4 the other direction. And just when you graph it, make it wiggle like sideways. All right, so what is this one called?
Exponential.
Exponential. I'm not going to write that all out. Exponential. It's actually my favorite one, and I always do this while I'm talking about it. You guys remember this? What shape did I call it? It's a swoop. Okay, there's a horizontal asymptote, typically at 0, but this one moved down 2. So you're going to dot that in down 2, and there is only 1 point you will be able to get without a calculator. Ooh, does anyone remember about what number E is? Because E is a number.
Oh,
I'll take that. 2 point something, I will take it. It's 2.718. I only know that because I live in this room and do math problems all day. But if you know it's a number and it's about 2 point something, you're good. I'll take it. Perfect. Okay. The only thing that you can plug in without a calculator is 0. And that is because anything on God's green earth to the 0 power, oh my gosh, I love you for not saying 0. It's 1. And then 1 minus 2 is -1. So that's the only point you can have. And I always bring this up in pre-calc. This is usually where everyone stares at me and goes, Miss Cole, we have an invisible line and 1 point. What on earth are we going to do? Well, it's going to swoop. So you have to know the shape and that it's going to do that. This one is logarithmic. Ln and E are inverses. So it's going to look like a swoop on its side. This one, did I move it left or right? Left 3. So instead of a horizontal asymptote, it's going to be vertical, and I moved it left 3. So for the exponential and logarithmic, you want to think about where the asymptote is versus points. You want to get the asymptote in the right spot. And then it's going to be on its side. Just like this one, the only thing you can plug in is 0. Anything to the 0 power is 1. Ln of 1 is going to give you 0. Let me write that out up here. e to the 0 gives you 1. But ln of 1 gives you 0. They're inverses of each other. Like 0, 1 and 1, 0. That's just a good thing to know. Or if you aren't sure, guess 1 or 0. Okay. Now, what would you plug in here to make this part be 1? So if you plug in -2, you would get ln of 1, which is 0. So -2, 0 is your single point that you can get. And doop-de-doop looks like that. I like this next one. Does anyone remember what it's called? Polynomial. I'm dyslexic though, so I spelled it wrong. Do you remember, does it cross, does it bounce, or does it wiggle?
Yes.
I know that, yeah, and it's basically just a pattern. I love these. So you can put on your graph, you can put a point at 1. So right there. And then you can put a point at -3. It's the opposite because it's what gives you 0. -3 plus 3 is 0. Now here's the only thing that's a little weird about these. You have to go right to left because this negative out front tells you that the right side is going down. I usually just draw an arrow. You can kind of do however works in your mind for you, but you have to go right to left and just make sure you match them up correctly. So when I connect to the 1, that's the one that has the 1 in it. Okay. Do you see how that's cubed? What does that mean I'm going to do there? Wiggle, like a cubic graph. So it's going to look like that. And then I always get, everyone's like, I can't draw that. And I'm like, do your best. Like, just make an attempt to get it to bend. And then what are we going to do with the -3? Bounce, because it's squared, like a parabola. So like that. How far up does this little bump go? No idea. Without a calculator, I have no idea. I know that there is a little hill there, or a maximum, but I don't know how far up it goes without a calculator. All right, rational graphs are a huge topic in calculus because we're going to do all of the behaviors of them. First thing you're going to need to do is factor this. I get that factoring is harder for you guys as a group because of when COVID hit you. All right. Numerator is going to be x and x. How would you split up the 2? 2 and 1. Good. 2 times 1. And then what symbols are going to go in there? Good. Okay, cool. We got there. And oh, you guys, I hear you talking through the problem. You're like already halfway there. All right, denominator, x and x, 10 is going to be 5 and 2. And they're both positive. Oh, this is, I hear you guys like going through it already. All right, let me get everybody back together here though. These cancel out. What does that mean?
Oh.
Thank you. Can you remember that until next week when we start talking about limits? That'd be great. Okay. So there's going to be a hole at -2 because -2 plus 2 is 0. How do you get the other part? Plug -2 back in. How do you get the output? Plug in whatever you have. -2 minus 1 be -3. I usually just write a little mental note. And then -2 plus 5 is 3. That's going to reduce to -1. So you have a hole at -2, -1. I have to tell you what, that is probably the best that has ever gone. Nice job. All right, there's going to be a vertical asymptote at where? This is what tells us, because you can't divide by 0. -5. So at -5, we're going to put a vertical asymptote. The horizontal ones are more difficult to remember because it's, well, if it turns out this way, then it's this. If it turns out this way, then it's this. Do you see how these are both squared?
That means it's the number.
That means it's the number out front. Now there's nothing there, so it's 1. So it's going to be 1. So it's going to level off at 1. if the numerator is smaller than the denominator, it is automatically 0. Good. And if the numerator is bigger, it's a, does anyone remember what these are called? Slant asymptote. So it's going to either go up or down. All right. And then the last thing is to get some points. What would make the numerator 0? 1. So we would have a point at 1, 0. So right there. And then this isn't really going to fit on the graph, but just for the sake of bringing it up, if you plug in 0 for all of those x's, I usually just cover them up. If you plug in 0, you get -2/10. That'd be -1/5. So it would be like right there. Do you see what I'm talking about? I mean, like 0 -1/5. It would be super tiny, but you know, for the sake of argument, it's going to look like this. So what delta math is going to have you do is do all those characteristics, like click here, click here, click here to put the things on there, and then it'll draw it all in for you. All right. Oh, I don't know why a V showed up there. That shouldn't be there. That's a typo. Sine and cosine. I just put sine on here. Do you remember what shape they are? Like what they look like? Oh, good. I love everyone just goes like this. The way I remember them is where they start. Do you remember where sine starts? Gosh, I love you guys. This is easy. Do you remember where cosine starts? All right, great. So we're going to start at 0 and then it's just going to wave. So you're going to go up to 1, back to 0, down to -1, back to 0. Don't put arrows on the ends because an arrow indicates going a single direction forever, and this won't do this. It'll just keep on waving forever. That was about the best that's ever gone too. Nice job. All right, I'm only going to have time for one of these, but that's okay because you're going to practice them on delta math. Piecewise functions are huge because we talk a lot about continuity and it's do the pieces match up. So let's just do one of these. I'm going to do 16 because it's probably the hardest one. The first piece is 5. That is a constant flat line, horizontal line at 5. But we only want to draw it from -3 to 1. Here, just watch me do this for a second. I'm going to go up to 5. 1, 2, 3, 4, 5. This would be a whole line of 5. But I only want it from -3 to 1. Do you see what I'm saying? Okay, so I'm just going to like erase the rest of it off of there. So it's going to be like a segment instead of a line. Now the question becomes open or closed circle. What do you want for the -3 part? Closed, good, because of the equal. And at the 1, open, because not equal. On delta math, you'll like click on it. Like you can toggle it. Do I want a closed circle, an open circle, or an arrow? Like if you just keep clicking it, it'll toggle through the choices. Now this is interesting. Just when x equals 1, so it's a single point, we want to be at -2. So it's the point 1, -2. So it's that floating point. So just a filled in circle right there. And I don't want the bell to cut me off, so we're going to have to do the last part after lunch. I'm so sorry. But it's going to be this line from there to there. What kind of circles will it have? They'll both be open. Actually, I'm going to draw it so I can stop the video, but it's going to be this line from there to there.